So this is a work about reinforcement learning. So we will have a state space, and then agent will decide which action to take at each state. And this decision rule is called policy. And then the agent will receive a reward and then transit to the next state based on the information of the current state action pair. So this process is Markovian. And then we also use a discount factor to discount later time steps. Here we are interested in policy evaluation. We want to see how good the policy is doing. So what we do is to compute some value function. It tells us, starting from some state action pair, how many rewards in total an agent can gain by following this policy. And this defines the Q value function here. It will be the cumulative discounted rewards in total along a trajectory. And for value prediction, we can just, for each state action pair, we can state its value. Then we will store a table for lookup. But the thing is, we can have extremely large state space. For example, in Atari. Like this Atari game, we say it's 84 times 84 pixels. Then on each pixel, it can have a different value. And the state space is extremely large. If we store every state into the table and store the value function, the storage is really huge. So what we do instead is to use function approximation. So we use function f with parameter theta to predict value functions. It takes input. It takes state action pair as input and output the predicted value directly. And here we give an example, linear function approximation. For each state action pair, it will have some feature vector phi. And the predicted value will just be the dot product between the feature and the parameter theta. And this linear function approximation will be the case this work mainly focuses on. And other than function approximation, when we do value prediction, usually we use bootstrapping. Why do we need it? So first, we are interested in value function, which is the cumulative reward along the whole trajectory. Then at each time step, the agent may take different state and different action. It has some randomness in it. And along the trajectory, the randomness will just increase exponentially. So we don't want such high variance estimation stuff. We want something with lower variance. And what we do here is use bootstrapping. It will use estimated values for other state action pairs to facilitate learning. And TD algorithm is such thing which using bootstrapping. Here we show one-time step lookup. A big white circle represents a state. A small black circle represents an action. And we are giving a transition from state action to the next state action pair. And we say, oh, why don't we just try to match our predicted value to reward plus the estimated value for this next state action pair. In this case, we only have one-time step randomness. And this thing is just called bootstrapping. And I also write down the temporal difference error for linear model. It will just be reward plus estimate value for the next state action pair minus the estimate value for the current state action pair. And value prediction is such a key component for RL. It exists in a lot of algorithms, including policy gradient things, including we want to evaluate policies. And TD is the most widely used algorithm. And another task we may be interested is to do it off policy. What is off policy? It means we want to evaluate a target policy pi, but we may not have data from it. We may only have data collected under some other behavior policies, mu. And why is this the case? Just we take self-driving car as an example. We have some human drivers. We collect some data from them. But then the agent proposes its own policy. We want to evaluate newly proposed policy. But we cannot say, oh, let's just execute this new policy and see what happens. It will be very dangerous and can even be life-threatening. So what we want to do is really evaluate this target policy with those pre-collected human data. And in this case, it's off-policy value prediction. It also exists, it's also important for other real-world applications, including surgical robots. And also, it's very important, even for RL itself, learning online. We can use experience replay buffer. We will have data collected from previously learned policies. And we will reuse those data to evaluate the newly learned policy. But the side news, okay, I also have a more formal definition for off-policy learning here. We focus on learning with a data buffer. It means we will have a data set with multiple transitions. And in this transition, the state action pair, they may be sampled from some distribution. We say if the distribution is different from the stationary distribution, then we say it's off-policy learning. And what is stationary distribution? You can just think it as the distribution of state action pairs where the agent will gradually converge to along the time. Just finally, the agent will sample state action pair from this distribution. Yeah, as long as the data distribution is not this one, we call it off-policy. And the side news are for off-policy value prediction, we may have some explosion risk, which is the deadly triad. One, these three things are combined together: functional approximation, bootstrapping, and off-policy data combined together, we can have instability. And why is it happening? We can see just the bootstrapping asks us to use estimated values. With functional approximation, this estimation may be inaccurate. And when we have off-policy data, we are using a wrong state distribution, data distribution. It means it's emphasizing some part of state action pairs with this distribution. And this part, they can have really large temporal difference error due to this functional approximation bootstrapping thing. And we are emphasizing them, and they can give us divergence. But if we are using the stationary distribution, we are emphasizing the right part, and this issue does not exist. So what we really want is to solve this deadly triad issue. Our work just say, yes, we find a solution. If we combine a target network and over-parameterization together, we solve this issue. I will introduce what are these solutions later, but basically, target network and over-parameterization, they are already just well-established, widely adopted methods for deep learning people. And with this simple augmentations, it means our solution can be applied to real algorithms and bring us new results, and really solve those off-policy tasks and also improve online reinforcement learning. Okay, so let's look into details for now. So first, we will study the deadly triad issue in more details, and we will see some previous solutions. So let's start with a two-state counterexample. We have left state and right state. And the value function for the left state is estimated by a scalar parameter theta. For the right state, it's estimated as 2 times theta. For each state, there is only one action, and the reward is labeled on the graph. And consider we only have one transition in the data set. It's coming from the left state to the right state with 0 reward. Because there is no reward observed, so the learned value should be 0, and theta should converge to 0 as well. And also observe that just in the data set, the empirical distribution will concentrate on the left state, but the stationary one will concentrate on the right state because the agent will gradually all move to the right state and stay there, so that will be the stationary distribution. So they are different. So it's off-policy learning. And when we already have functional approximation of policy learning, and when we combine it with bootstrapping, with TD, the algorithm diverge. Here the divergence will happen for any discount factor larger or equal to 0.5. So this is, I'm showing you the deadly triad indeed exists. So what solution can we have? Some people say, oh, let's use target network. It's introduced firstly by deep learning people, deep reinforcement learning people. And they observe that it improves the stability empirically. We also have a theory work telling us, oh, the deadly triad can be broken with a target network. And what is it? So I mentioned that we use bootstrapping. Bootstrapping means we use value estimations for other state action pairs. And here just with the target network, we will evaluate those bootstrapping value using the new target parameter. Instead of the original parameter, we call them student parameter. So basically, in the temporal difference value, some part is switched to the target parameter, and that's the only difference. And how are we going to update this new target parameter? It will be initialized the same as the student parameter, and it will be updated every m steps by directly copying the student parameter. So it's like when we compute temporal difference error, the value estimation for the current state action pair will use the current value of the parameter. But when we evaluate for other state action pairs for bootstrapping, we'll use some previous parameters from m steps ago, like that. Yeah, okay, perfect. But what we figured out is that, no, that the target network didn't solve our issue. Actually, for no matter what just the update step we choose for the target network, just basically the m step thing, no matter what m we choose, the algorithm will always diverge. So why is it happening? Is this paper saying a wrong thing? Actually, no, just because their proof is only for a modified TD algorithm, which project parameters into a bounded space. So they modify the algorithm and finish the proof. But we don't want this step. Projection will slow down the learning, and how are we going to project a neural network? So it's actually not a practical solution. And other than divergence, the deadly triad issue have more damage. Sometimes the fixed point may not even exist. We still look at this two-state counterexample. When gamma equal to 0.5, the known state, the known form of the TD fixed point will rely on zero inverse. And we know that the multiplicative inverse of zero does not exist. So if the fixed point does not even exist, where are we converging to? We try out it empirically. It seems like TD will just be stuck at any initial value it has. And how do we solve this non-existence issue of the fixed point? People suggest, yes, we can use regularization. But the thing is, maybe it's not a perfect solution. Paper just figured out TD with regularization can give us worse parameters than just the zero values. Just those learned parameters, they predict even worse than zero. So it's actually not helping. It's not the solution we want. Then how are we going to solve this non-existence issue? So maybe we can use some intuition here. Let's think about a linear system. When we want to solve a linear system of equations, just ax plus by equal to c something, a system of that. Just the solution may not exist when the model is overdetermined. It means we have too many equations, too less parameters, and some equations, they may contradict each other. Then the solution does not exist. But if we increase the number of parameters, we have more parameters than the conditions, then the solution definitely exists. So putting it back to deep learning, to TD, it means, yes, how about we just have a model? So we have more parameters than the number of training samples. Yeah, basically training samples are similar to those equation conditions, and parameters will be the solutions. And now in this time, oh, they should exist. And let me just talk about this over-parameterization model more first. Basically, when we have more parameters, it means we can give them, we enable the model to give zero training errors. Every training data point is well expressed. And for a two-layer neural network, if we have n samples, each of dimension d, as long as we have more than 2n plus d parameters, the model is over-parameterized. And this over-parameterization thing is not overfitting. It feels almost like that. We all seen that picture. We only have 5 data points, and we gave a polynomial of 100 degrees and overfit the data. But that's not over-parameterization. It has been observed empirically that over-parameterization improves both optimization and generalization. And also some theory people also prove that over-parameterization indeed have some benign optimization property, such as stochastic gradient descent. They achieve the fast convergence rate as full batch gradient descent. So basically, that's an introduction to over-parameterization. Let's come back to TD. We wanted to solve the existence issue. And this paper basically proves us there are infinitely many solutions which give us zero training errors, but TD indeed converge to only one of them. And that convergent point always exists. So yes, over-parameterization solves the existence issue of the fixed point. But the thing is, does it solve the deadly triad? The bad news is still no. Let's look at the famous Baird counterexample. Here we have 6 states, but only a dimension of, but a parameter of dimension 7. So more parameter than the data set. Then the model is over-parameterized. And in this data set, and also same again, just for each state, we only have one action, always 0 reward. And the model is linear function approximation. How a value will be predicted is written on the graph. And we consider a data set where each transition shows up once. So in this data set, all states, they are sampled uniformly, still not a stationary distribution. Stationary one will concentrate on the last state with the self loop. So it's still self-learning, still off-policy learning. And in this over-parameterization model, TD still diverge. So it basically tells us, no, over-parameterized TD does not solve our issue. Then what should we do? We tried 3 things: target network, regularization, over-parameterization. They all didn't solve our deadly triad issue. What should we do? So first thing, maybe we want to keep the over-parameterized setting, because at least it guarantees the existence of a fixed point. And then how about we just add target network back? And that's what this work found. The combination of target network and over-parameterization model solves the deadly triad. So first, let me show you some evidence on the Baird counter example. So we really test out the over-parameterized target TD. And now we can see it stabilized the learning. And the value prediction errors goes to 0. So it's a good sign. But we need proof. It's just empirical evidence. It's not a proof. So we want a more rigorous statement. But for the more rigorous statement, we will need a lot of notations. Sorry for that. Here we first focus on expected updates. It means the data set will cover all state action pairs. And to have an over-parameterized model, we need the dimension of parameter D to be larger than the total number of state action pairs. And we will define a feature matrix phi. Each row will be the feature for one state action pair. And then D, and then go to the second line, we also define the D matrix. It's a diagonal matrix. It's diagonal just equal to the empirical distribution in the data set. And then we define the transition matrix under the target policy pi between state action pairs. We still have the theta parameter, we call it student parameter, and we have the extra one, the target parameter. And if we look at the update rule, just for over-parameterized TD, we will just take a semi-gradient of mean square error of temporal difference, mean square of temporal difference error. It will give us the update rule there. But for over-parameterized target TD, we will add in target network. It means when we compute the temporal difference error, we will bootstrap using the target parameter. Target parameter initialized the same as the student one, updated every M step. And what did we figure out? Oh yeah.
What is pi?
Phi is the feature matrix. Pi is the target policy. Yeah. And recall that our definition of policy is as long as the data distribution is different from the stationary distribution of pi, it's off policy. So D is something unrelated to pi and make it off policy. Yeah. And then let's look at the proof. The theorem. So first, we copy a proposition from the previous work. They tell us over-parameterized TD converge, but with some condition. It requires the spectral radius of a matrix to be smaller than 1. What we figure out for our work is that with the help of the target network, that condition can be removed. And now basically it's claiming, as long as the over-parameterized model, there definitely exists hyperparameter choice such that the algorithm always converge for any task. Then this just theoretically support our statement. Yes, we indeed find the solution. And let's look at the property, maybe look at the property of this fixed point. Oh, yeah.
There must be some catch here, right? You cannot just...
Yeah, I feel the most important thing is to notice that we prove it converges without conditions. And the second thing is about the fixed point.
There's still some condition, right?
Yes. there are still some conditions on the hyperparameter choice, like on the learning rate eta, and the update window size m for the target parameter. But we basically claim here just as long as we do hyperparameter tuning, we can definitely find the right hyperparameter. It's not like the previous result. Previous result is like, oh, even we search along, we find the best hyperparameter. There always exist tasks where the algorithm can diverge. Here it's like, no, as long as we do good hyperparameter tuning, the algorithm is guaranteed to converge.
What is M bar?
Oh, M bar is basically saying,
What's the expression? How does it go?
oh, we only prove the existence of M bar. We didn't really find the closed form of M bar. But it's basically saying just for some target value large enough, target update window size large enough, then this thing will hold. So if the algorithm diverges, then just increase the number of this window size. Keep increasing them, you will find a good one.
And that will slow down the convergence as well?
Oh, yes. It's not about slow down the convergence. It's about finally we get convergence. Yeah, go ahead, Michael.
Yeah, I can't quite tell if this, and I'm going to use the word just, and that usually sort of puts something down. I don't mean to put this down. But I sort of wonder, is this sort of saying, okay, the over-parameterized regime is almost like saying, okay, we can get to almost the case that we're tabular now, because we can represent, in some way, just a parameter for every state action value. And the target network is saying, we're like so big, the M parameter is like saying, we're so big that we're gonna like update all the state action pairs at once. And so like, is it okay to think about this theorem as saying, under the right conditions, we can just get to essentially like synchronous value iteration?
So what do you mean by synchronous value iteration?
I mean, like, forget about experiencing the world the way reinforcement learning does. You could just say, I have a complete model of the world, I'm going to do value iteration in the sense that I'll take every single state action pair and just update it using dynamic programming so that the value of this state becomes the value of the expected value of the next state plus the total.
Oh, I see what you mean. Oh, so first thing is this result is limited to expected updates. It means each update already used all state actions. But the result is not limited to this case. Just we gradually figure out when the data set does not cover all state action pair, only part of them, the convergence still holds. And then for the over-parameterization part, you see it may be just something similar to tabular. But the thing is, if it's really tabular case, then over-parameterized TD should converge, but actually not. So it means over-parameterization actually is still functional approximation. And the thing we realize is it's just something work very different from the under-parameterization thing. Like here we have, if you look at the fixed point, first we have a pseudo-inverse of the feature matrix. It almost serves like a projection matrix. It means when we want to do functional approximation learning, we need to project everything onto the row space of current features and then do prediction, do generalization. It's still some functional approximation, but a different mechanism. And the second thing is about target network. You ask just, I'm looking for extremely large update window. Does it mean?
I guess you're into, like when you described it, you said there's an integer M bar, and then you later said, well, there's a sufficiently large. This made me think, oh, like all you're really doing is more pejorative than I mean. This is still very interesting. but I mean, like, there's an interpretation of that just says make the target network big and like long enough between when you update it that you really are just like you're just doing value iteration. You're doing a sequence of steps of dynamic program value iteration. And as long as the target window update is long enough, then you can view it that way.
I can ask you that. I think your insight is great to connect it to dynamic programming. I want to say that even without target network, this is already dynamic programming. This is just expected update.
Right.
And
the fact that so maybe what's really throwing me is that over-parameterization wasn't enough. And understanding the difference is maybe more is where I want to understand.
Over-parameterization with dynamic programming will still diverge on this counterexample. You still need target networks for dynamic programming. That's the part.
Oh, and also another thing, just this one does not have over-parameterization, but it basically say, oh, we increase the target network to infinity size. It's already doing something like value iteration, but the thing is, value iteration in our policy does not necessarily mean convergence. So it's not really the use of target network is not about change it to value iteration. The effect is like, because we have target network, like a delay of M step, and this M step, they can be combined together. And when we try to combine this M step together, we introduce a new matrix B. And this B, so my intuition is like, by combining M step, target network links us to some matrix-based, links TD to some matrix-based method. And that's why we are getting good properties. That's my intuition. No problem, thanks. Oh, okay. And then next point is about the property of the fixed point. So if we look at the fixed point, this one is for initial value 0. The fixed point equal to the pseudo-inverse of the feature matrix times inverse of I minus gamma transition matrix times the reward function. The surprising thing is it's independent of data distribution. And it's just because it's over-parameterized, just every point they can be independent, not independently, just their self, they can be well expressed. So data distribution doesn't play a role here. But this is a really just amazing result. It just tells us the value prediction error bound for off policy can be bounded by how well linear function approximation can do to evaluate true value functions. And if we look at the result for on policy TD fixed point in the under-parameterized setting, we can see the two error bounds, they basically match each other up to a constant difference and a norm difference. But recall that for on policy TD learning, we require the data distribution to the stationary one under the target policy pi. Here we have a result for off-policy learning. So I feel this is a really just a new result, a new breakout for off-policy learning. And with the help of this independent of distribution thing, we can do other things later. But we will talk about it later. Yeah, here.
Yeah, so the difference here is just a factor of 2. That's what you're saying.
Yeah.
Like the cost of doing off policy is just 2.
Yeah.
Okay, cool.
Oh, and yeah. Then what we want to say is,
Not exactly.
yeah, also the norm difference. Yeah, the norm difference, infinity norm is even better. It's the worst case bound. It bound the norm for the worst reaction pair. It's even better than the distribution bound.
I thought it wasn't, because maybe you're off in just one place, and d pi doesn't care about that.
Yeah, but infinity norm care about it, and now we can bound the infinity norm. Yeah. And what we want to see, we already, oh, yeah, go ahead.
We have a question in the chat.
Okay.
I don't know if you can see it. Yeah, you can just read it out, please.
Oh, the question is there any assumption on the feature matrix? I guess we need a feature matrix that has rank equal to the size of selection space. Oh, yes. The answer is yes, we indeed need the feature matrix to be full rank, but it's really intuitive. Like if we, for two selection pair, if their features, they are somehow correlated, they are just the like feature for some selection pair is just 2 times the feature for another one. Doesn't really help with the learning. Just so we actually require the rank to be full rank. Yeah, thanks for the question. Oh, and we have showed you we have a solution to solve the deadly triad. And we told you, oh, it's just simple augmentation, so it's practical. And we prove it theoretically. But the thing is, it's not the first solution. Previously, people have come up with algorithms which solve the deadly triad. For example, least square TD. I show the algorithm here. You don't need to really look through it. You just need to look at line 2.1, matrix A. They need to really estimate a matrix of dimension D square. They need to store it, estimate it, and then invert it. So it makes the memory and computation requirement to be d squared. So our algorithm is much more efficient than it. And other than that, we have other solutions, including the family of residue minimization algorithms and the family of gradient TD algorithms. So first thing, our algorithm is OTTD, shown on the top row in the middle. And then we can see that our algorithm is much faster than others. Especially notice that the training step is in the log scale. So it means residue minimization is 1,000 times slower than our algorithm. And also, their slow convergence rate is the reason why they are not widely adopted practically in the field.
The first one is the mix is going up, the other going down. You're trying to take a large byte or small byte?
Oh, we are trying to get a small value. The y-axis is the value prediction error. We want them to converge to 0. And the first one is over-parameterized TD.
And that's why it's cool.
Yeah. So now, great, we have a practical solution. And then the thing is, we only show it for expected updates. That's one, the data set covered the full state action pair. How about one, the data does not cover all of them? So in the general case, we'll just have a data set with transitions. In this case, we have a convergence proof, but with some condition. Then we look at a special scenario where the data set consisting of trajectory data collected under behavior policies. And this trajectory data can be broken into state action pair, next state action pair transitions as well. And for the over-parameterization model, we just want to count just how many state actions show up in the data set without any repetition. Just some data they may repetitively show up, but we do not count them. Just say how many data samples in total it shows up. We call that K. And we just want our model dimension to be larger than that K number that is over-parameterized. And then we will focus on this special scenario with trajectory data. So first thing we need to do data distribution correction. And we already mentioned, because it's collected under completely different policy. But we have mentioned that a good thing of over-parameterized model is that we do not need to worry about data distribution. So here we only need to correct the distribution when we sample the next action at the next state. So we only need one step important sampling correction, and it is enough. And what we do is to reweight each transition by the corresponding policy ratio, which equals to the ratio between the target policy pi over the behavior policy mu. And this reweighting changes to, oh, yeah, go ahead.
If you were just wanting to do, like, find the optimal value function so that you were doing, like, Q-learning, could we then drop the important sampling correction altogether? Because there is S prime.
Yes.
A prime doesn't come into play at all.
Yes, that's what we also proved, just for Q-learning. But the thing, yeah, the thing is, for Q-learning, we do not need any correction. They just converge. Yeah. Yes, and with this important sampling reweighting, we change two parts. One is data distribution, empirical data distribution, because all transition is reweighted, but it doesn't matter. The second thing is it reweights transitions. So for each transition estimator, it's corrected by the important sampling correction. And the thing is, with this reweighting thing, the denominator should not be the occurrence of the state action pair. It will be the sum of corresponding important sampling ratios. It basically realizes normalized important sampling, which gives a lower variance even than per step important sampling thing. And with all this correction, we can now evaluate value functions for the target policy. And another thing we add to our algorithm is now we have trajectory data. We want the last state to have 0 value to bootstrap on, to stabilize the learning. Actually, to avoid extrapolation, because those last state, they may not be trained on. They don't have any transition for them. So they are never trained, and we don't want extrapolation. So we just set them to value 0. And it hopefully doesn't bring us much error, because the trajectory is really long, and this time step is discounted. So if we only set the last state to 0 value, The error, we hopefully it's very tiny. And what we do here is not directly setting the value to be 0. We add in loop transitions because it makes the proof more convenient. We just say last state will self-loop back to itself with zero reward. So it's equivalent to say it has value 0. Yeah. And with normalized importance sampling and this loop transition, again, we show the convergence proof. The thing to notice here is, again, there is no condition. We only say, oh, there definitely exists hyperparameters, and the convergence hold. Even it's offline learning with partial data coverage. Still, we can gain convergence to a reasonable fixed point. And also, it's showing the paper, we can bound the error when we try to approximating the true target value. Yeah. Oh, and then the thing is, we push it to Q-learning. We only have a batch of data. We can do TD learning, and Q-learning is also such kind of temporal difference learning algorithm. What happened with Q-learning? The result is great, just it still converge. But because of the data limitation, just the data set basically defined as a truncated MDP. So it will only converge to a value, optimal Q value defined by that truncated MDP. And we don't really know just that truncated value, how, what kind of policy that truncated value will present us. So we only know it converge, but we don't know how it performs. Okay, so in conclusion, it's very simple, just with expected update. When the data set cover all 3 action pairs, OTTD solve the deadly triad without conditions. And then with a pre-collected data set of off-policy trajectories, OTTD just needs the help from the additional loop transition and per-step normalized importance sampling correction. Then it can successfully evaluate target policy again. And then for general offline data set and policy optimization, over-parameterization and target network still enhance the stability, but the convergence has some condition. And that's all. Thanks for listening. Yeah.
Can I go first? Yeah, you. I don't ask. So I'm the non-expert. Is tabular is the special case of over-parameterization, or is that a minimal over-parameterized model? Tabular representation. Because you can always represent it as if it's the first stage, if it's the second stage, then it becomes the minimal over-parameterized model. Am I right?
Yeah, I think so. Just when the dimension is equal to the number of data points, it's still over-parameterized model because it can still give us 0 training errors. But it's still very different from tabular because in tabular, we really need to store state action information and search among those storage. But with the over-parameterization model,
represent tabular, the value or whatever value, Q value or whatever value, as a linear transformation where the weight is just the value, and then my feature is just one hot representation, which state it is. I just retrieve the value. So what I feel is the tabular case is a special case of the over-parameterization.
oh yes, it is. Just one hot encoding definitely gives us over-parameterization model, and tabular is one of such model. The only thing is, usually for over-parameterization, we don't like one hot encoding because we still want some generalization to happen. So it's
the question is,
yeah.
Why does the generalization happen? For example, in linear regression, if I throw in some random features, it doesn't generalize to new data. But for the over-parameterization generalization, I feel most of the results are for, let's say, neural networks. So there's something magic happening with neural networks. I don't know if you can do generalization for linear regression models. You just throw in some random features that they generalize.
Actually, I don't have an answer. But I only have some, and also I know nothing about deep learning. But I have a feeling here for that over-parameterized TD. So what the model is doing is that just when we want to predict value for some feature, it's like we have a data set. This data set, it already gives us many features. And when we have a new data point, some feature, and what the model is doing is it will project this feature onto the row space of that defined by the data set first, and then and then use the projected coefficient to do the prediction. So that projection part already say, oh, how this new vector is aligned with each previous features, and do the generalization.
So your proof is mainly about the optimization or the convergence of the optimization. Do you have any results, empirical results or failures of generalization? Does it work for new scenarios?
I test for generalization, but I didn't test for new scenarios. I only test when the data set only covers some state action pair, but I have new state action pair, what happens.
So it works for generalization, like your approach?
Yeah, and the result is like the error is bounded, but we actually just we can see the error is comparably small, but we don't know how really good the generalization is. And also more than empirical result, we also have theory result. Just when the data set only cover part of state action pairs, we have a bounded error for among just all state action pairs, even for unseen state action pairs. Yeah.
I would like to follow up more on this connection between value version, but that's not the question I want to ask you. Right at the end, you said, can you go back to your slide you're reporting?
Conclusion. Before.
Maybe it's just not what you said. What did you say about Q-learning? You said.
I said like the algorithm with a batch of data will still converge, but we didn't really see what is the quality of that fixed point.
Okay, never mind. I now remember one question. Sorry, it wasn't this. That was a separate one. Sorry, the question I had was on the expectations. So you were talking about doing expected updates.
Yeah.
Do you think that's a limitation of your theoretical, like the mechanism you're proving, or do you think that's a limitation of if I dropped expected updates, this wouldn't hold?
First thing is like it's using expected update. It means it uses batch update, just the whole data set to update. Yeah.
So what if we did more SGD, like mini batch or mini batch mean size 1?
Yeah, let me.
Do you think that your proof technique fails or the algorithm fails?
Let me maybe tell others. So first, this full batch update thing is not a bad thing. It's what PPO is doing. It's also commonly adopted. And the second thing about your question, that's the extension of the work. We are working on it. And we feel like the proof set, we need new techniques, but the results should still hold. Like because people have results like stochastic gradient descent work as full batch gradient descent with over-parameterized model. Then why with TDA it doesn't hold? So we guess it should still be a promising direction.
So when I just wanted to clarify, was that restriction like you need it or you just don't know how to relax it yet?
We didn't work on that yet. Yeah, thanks.
Isn't it obvious, like, use the usual Porter proof, expected update works, so under very reasonable conditions, variance is bounded, or something, the per step update stochastic update will also work. Isn't that
something sounds like the extension?
No, it's like very reasonable assumptions, mostly on noise and if the errors are not too correlated. So make a martingale assumption and then it works. Like, isn't that trivial? Just 2 lines in the paper and done.
The thing is to bound variance is already a hard thing. I think for stochastic approximation proof, bounded variance, I feel is already the hardest part. Yeah.
Do you have an explanation for why over-parameterization by itself isn't enough?
Isn't enough.
Yes. So you said that we need over-parameterization and market network. So do you have an explanation why just over-parameterization itself is not enough?
Yeah, my intuition is like, because it's intuition, so it's not rigorous. It's like, it's still, just as we discussed, it's still a kind of functional approximation. It's not tabular, just something like projection, neural network stuff, it's still going on. And that makes the data distributions, not data distribution. Yes, which part? Yeah, basically that's still just we didn't really eliminate the functional approximation part. Yeah.
And then you have a function that can bring your feature from the lower dimension to the high dimension, and then it should be able to capture every set of features if there exists such a function. So by itself is over-parameterization. You should know.
Yeah. Like.
My question is.
This is related to the larger conversation I want to have. I was thinking about having offline, but I do see a difference, right? In tabular setting, you can set the step size so that you can get all the way to a single step of value iteration. Right? If you set the step size to 1, then you get entirely value iteration. That is not true in just the general over-parameterized setting, right? Like you point a gradient, but what we know is if you follow the gradient eventually to a global minimum, then you're doing a step of value. That's like doing a step of value iteration. But one single gradient step is not. And now I'm wondering, is putting in target networks, slowly changing now, allowing you to do many steps of gradient descent so that you can actually get to doing, so this is trying to, I think, make the standard target network, like the target network is kind of making a gradient descent neural network space look more like value iteration. I still claim that might be true, but I was trying to answer maybe what the difference is. The difference is in a tabular setting, the direction you point is directly to the target. And once you have a network that even if it's over-parameterized, there might be a winding path right there. And so a single step of gradient descent can't do it. But maybe this is, I could be wrong too.
No, I feel Michael gave the perfect answer. And for your question, I still don't really know just the word target network. But mathematically speaking, it's like the update rule can be written this way. And for TD, for over-parameterized TD, the C may have larger, just like negative eigenvalues. Then it makes the convergence matrix has an eigenvalue larger than 1 and causes a divergence. It sounds like the gradient step is too large. But with the help of target network, it's like we combine multiple C together, MC together, and it makes the this eigenvalue positive. And then, in this way, it sounds like what you are describing.
Yeah, if I'm right, there's got to be a connection between that and that, is what I'm saying. I do not know what that connection is. So that doesn't explain it.
Yeah, but to value iteration, I can also see value iteration as well. Just I feel when target network goes to infinity, it is value iteration. So basically, what we prove is that in the middle of TD and value iteration, target network lies in between and already help. Yeah.
Okay, that's fair.
Thanks. Oh, yeah, question online. The question is, I'm wondering, what do I mean by solving the deadly triad? Basically, by solve the deadly triad, we are saying for each task, the algorithm can always be tuned in a way such that the algorithm converge. Yes, we still have conditions on the hyperparameter, but we can show they exist. So as long as the learning rate is small enough, the update window size is large enough, then this algorithm definitely converge. I feel it's a fair statement because usually when people say convergence proof for optimization algorithm, they do not say, oh, it holds for all learning rates. They say the algorithm holds for some learning rates. So it's still, we have no condition on the task or the data set. That's why we are saying we solve the issue. Yeah, thanks.